Alright, so today we're going to talk about motion on inclined planes, meaning objects that are moving up or down a ramp. And we're going to try to add friction into the mix and see how all of this works. So basically what we're looking at here is an object that is sliding down a ramp. And for now, to make things simple, we're going to say that the ramp just looks like this. It's got some angle theta that the ramp is at. The object is on that incline. And the force of gravity is acting downward on that object. One of the problems that we have, though, is that the motion of the object is in two dimensions. And dealing with this problem would be very difficult if we needed to split the motion of the objects or the motion of the object into two different dimensions, and we have to treat everything separately, and it would not be very fun. So we're going to employ a little trick here, and this is something that we're always going to do for inclined plane problems. What we're going to do is we're going to try to define our coordinate system so that the coordinate system actually lies along the incline. So the y direction of our coordinate system is actually perpendicular to the incline, and the x direction of the coordinate system lies along the surface of the incline. The difference now is that the force of gravity in our new coordinate system is in two dimensions. So what we'll end up having to do is to split the force of gravity up into two components. One component that's in the y direction, which is perpendicular to the surface of the incline, and another component that's in the x direction that is lying along the incline. Doing this will allow us to solve these problems much more easily, but we're going to need to figure out how to decompose that vector into the x and y components. This is a little bit different than we've dealt with before. We know the angle of the incline, but we don't know the angle of the force of gravity inside our new coordinate system. Kind of a complex idea here. So what I'm going to do over here is to derive the equations for the components of the force of gravity in our rotated coordinate system. I'm going to start by drawing the triangle that represents our incline. So it's right there. Here's theta. That's going to be a right angle. The next thing that I'm going to do is I'm going to draw the force of gravity vector, and I'm going to start it here on the incline and just go down like this. Okay, so that's the force of gravity. Now I'm going to do the x component, the y component of the force of gravity, which we said was perpendicular to the surface of the incline. And then I'm going to add the x component, which we said was parallel to the surface of the incline. So there's a couple of things that I know about this diagram here. This line here is parallel to the force of gravity vector right here. These two lines are parallel. If you remember a little bit of your geometry, if you have a triangle and you split the triangle with a parallel line right there, then these two angles are congruent to each other. So I can say that this angle here and this angle here are congruent to each other. The next thing that I can say is that the vector right here, which was the x component of the force of gravity, we said was parallel to the surface of the incline. I'm going to redraw that over here again. So here's the surface of the incline. Here's the x component. We said they're parallel to each other. And then we have the force of gravity vector, which was straight up and down. And we found that angle right there, which was the same as the angle, the upper angle in our large triangle. If you look here, this is two parallel lines cut by a transversal. We know more information about that from a little bit of geometry. We know that alternate interior angles are congruent to each other. So that angle is congruent. In our diagram, that's the angle right here. This angle is 90 degrees, so the only angle left in our little diagram right here is this, and so it means that that angle is actually theta. Alright, so I'm going to redraw this diagram a little bit bigger here. It looked like, let me erase that. So our right triangle looked a little bit like this. That's the force of gravity. There's the y component and the x component. So here is the force of gravity. This was the x component of gravity, and this was the y component of gravity. And we just figured out that this is the angle theta. Using again a little bit of geometry, we can figure out that the x component of the force of gravity is actually equal to the force of gravity times sine of theta. It's different than what you're used to. When we were dealing with any other decomposition of vectors, usually cosine is related to x and sine is related to y. Because of the rotation in the coordinate system, the x component is sine and the y component is cosine. So this is a little bit strange. You will not need to remember how to derive these formulas, but you will need to remember that on an inclined plane, these are the formulas to use to find the x and y components of the force of gravity. Okay, you can think about this as a system where maybe the angle theta is changing. The y component of the force of gravity is the component that's perpendicular to the plane. If the angle was 0, then the y component would just be the normal force. If the angle was 90 degrees, then the y component again would be perpendicular, but it would be perpendicular to a wall, and the normal force would be 0. If we look back at our equations, that makes sense because the cosine of 90 degrees is 0. So these equations make sense physically for what should be happening. Okay. Anyway, let's try to apply what we've just learned and solve a problem. So we're going to look at example 17 in your book. In this situation, we've got something that's moving on an incline. The incline has an angle theta, and we're told that the object is moving down the incline, and I'm going to call that the negative direction. If it's moving down the incline, the force of, if it's being pulled down the incline by the force of gravity, then the force of static friction is going to be resisting that, so it'll be upward. And downward will be the x component of the force of gravity. Alright, so some of the things that we know about this problem: theta is equal to 10 degrees. The coefficient of static friction that's keeping the block from moving down the ramp is 0.35. The acceleration max is what we're after. We're trying to figure out the car that's moving up this ramp, what is the maximum amount of acceleration that it can have without the tires slipping. If the tires aren't slipping, then it's static friction, and the acceleration comes from the amount of force that the tires are exerting on the surface of the ramp. So we'll need to use our knowledge of static frictional forces to solve this. We're not sure what the mass of this object is. If we look in the x direction, we know that the net force in the x direction will be equal to the mass times the acceleration in the x direction. The forces that are acting here are the force of gravity in the x direction and the force of static friction in the x direction, and that's equal to mass times the acceleration in the x direction. I can write all of this out and say that the force of gravity in the x direction is actually negative, so that'll be negative mass times gravity times the sine of theta. Remember, on an inclined plane, the x component of gravity is sine of theta. And then here the coefficient of friction is going to be the static frictional force is going to be the static coefficient of friction times the normal force, mass times gravity, but times cosine theta. Remember that the y component of gravity here has the cosine theta instead of sine theta. Okay, so what we've done here is to say that the y component of gravity is equal to mass times gravity times the cosine theta. And we're using that again as our normal force. All of this is going to be equal to the mass times the acceleration in the x direction. So again, you can see the mass of the truck doesn't matter because I've got mass and I can just divide it out from the equation, and I'll get the acceleration in the x direction is equal to the gravity times sine theta, negative, plus the coefficient of static friction times gravity times cosine theta. If I plug in all of the values here, I'll get negative 9.8 meters per second squared times the sine of the angle, which is 10 degrees, plus 9.8 meters per second squared times 0.35, which is the coefficient of static friction, times the cosine of 10 degrees, and that comes out to 1.68 meters per second squared. So the most acceleration that the truck can have while going up the ramp without its wheels sliding is 1.68 meters per second squared. If it tries to accelerate faster than that, the force delivered to the tires will be higher than the force of static friction. It'll exceed that maximum force. It'll go into the force of kinetic friction, which will then result in the tires slipping. Your homework is going to be problems 41 and 81, dealing with these. If you have any questions, you can see me after school in the lower school science lab.